Okay. Are you there, Shravani and Rukmani? Am I audible to you both?
Yes, sir.
And is the screen visible? Screen కనబడుతుందా? Screen is visible?
Yes, sir.
Okay. So today we'll look at 2 points. One is vector quantization. The other one is support vector machines. If you remember last time, classification and regression trees and k nearest neighbor videos were shared with you for learning. So today we'll just make a walkthrough on these two topics, vector quantization and support vector machines. So I'm directly using this textbook, Mastering the Machine Learning, by this Jason Brownlee. Okay, so the first topic being discussed using this Jason Brownlee's book is learning vector quantization. Here, there is a relationship between learning vector quantization, the short form is LVQ, with k nearest neighbor. You can say learning vector quantization is as extension of k nearest neighbor overcoming its deficiency or disadvantage. What is the disadvantage? K nearest neighbor, as you remember, it has to rely on the entire training data set. While LVQ is an algorithm which is an ANN algorithm, artificial neural network algorithm. So that will allow you like how many training instances you want and what those instances should like, all that. Now coming to model representation of LVQ. So you should remember a keyword called as codebook vectors. Codebook vectors. Okay. So LVQ actually is a collection of codebook vectors. Okay. LVQ is a classification algorithm. It supports two classes. It supports multiple classes. What exactly is a codebook vector? It is just a list of inputs and output attributes of your training data. Okay. So the model representation in LVQ consists of a fixed pool of codebook vectors. You have fixed pool of codebook vectors. Now, in neural networks, these codebook vectors are called as neurons. Okay. So each attribute on this codebook vector is called a weight, and the collection of codebook vector is called as a network. So we are introducing these many terms here. One term we have introduced is codebook vector. The other term we have used is neuron. And the other term we have used is weight and a network. Okay. What is a weight? Attribute on a codebook vector. And what is a network? Collection of codebook vectors. Now, how do I make predictions using the LVQ model? Okay. So it is similar to k nearest neighbor. Okay. So for a new instance, predictions are made. Usage of codebook vectors is done for k most similar instances and summarizing the output variable for those k instances. Predictions are made usually with k value being kept as 1, and the codebook vector that matches this value is called as BMU. The BMU is the short form for best matching unit. To identify similar instances of the training data set with the new instance, we'll be using the Euclidean distance measure. We know the formula for Euclidean distance measure also. Now, how do I learn in an LVQ model from the data? The LVQ algorithm, it learns using the codebook vectors from the training data. Now you have to determine first how many number of codebook vectors you want. It can be 20, it can be 40, and so on. Initially, the learning algorithm will be taking a random codebook vectors which are randomly selected. Okay. The codebook vectors have the same number of input attributes as the training data. They also have an output class variable. Now, these instances are processed one at a time. The most similar codebook vector is selected from the pool. If the codebook vector has the same output as the training instance, the codebook vector is moved closer to the training instance. If it is away, it is moved further away. Now, by how much amount this vector is moved is controlled by a parameter called as alpha. That alpha parameter is called as a learning rate. Okay. Now let us say you have an x variable on the codebook vector. It is moving closer to the training input value, say by a learning rate alpha. Okay. And it will be represented as follows: x is equal to x plus alpha into t minus x. Suppose it is moving away, it will be x minus. It is plus, it is minus. Now, this will be iterated, repeated for as many input variables or as many instances are there. Okay. Each iteration of the training data set is called as what? It is called as an epoch. Okay. The process is repeated for a number of epochs we must choose. So that amount of epochs or the number of epochs we choose is called as max epoch. That max epoch value can be 2000, 200, 20,000. Now, you also have to choose a learning rate, that is the initial learning rate, say 0.3. Okay. The learning rate decreases with each epoch. Okay. So initially the learning rate will be high, and as we iterate, as the epochs increase, the learning rate decreases. Now, the learning rate is calculated using this formula: alpha multiplied by 1 minus epoch divided by max epoch. Now, this learning rate is for the current epoch. Okay. So 0 to max epoch minus 1, the number of epochs. What the alpha indicates the learning rate. Okay. It will be given to the algorithm at the start of the training run. Max epoch is the total number of epochs to run the algorithm. Now, how do I prepare data for LVQ? Okay, same as you prepare for k nearest neighbor. Okay, in classification, LVQ is a classification algorithm. It will work fine for binary as well as multiple classes. This technique has been adopted for regression. Multiple passes. So using multiple passes is a good habit. Okay. So start with higher learning rate, go down. Then you have multiple best matches, which is the extension of LVQ select multiple best matches. Then you can normalize your inputs between 0 and 1. Okay. So why we normalize? Because there is a chance that an attribute may dominate the distance measure. If we normalize, then our initial values of the codebook vector can be between 0 and 1. Feature selection also is a measure which will reduce the dimensions, which can improve the accuracy. LVQ also has something called as curse of dimensionality, which we also had seen in k nearest neighbors. Now let us directly see an example of LVQ, which will help us understand the concept directly. So I'll directly take you to the example tutorial in this book by Jason Crowley, Mastering Machine Learning. You have here, see, there are two classes. One class is 0, the other class is 1. So it's a binary classification problem or a two-class classification problem. Okay. How many variables are there? There are two variables. What are they? X1 and X2. Okay. And there is a class variable called as Y. The class variable has how many values? Two values, 0 and 1. It means there are two classes. How many records are there? There are 10 records. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 data sets are there. Okay. Okay. 5 belongs to class 0, 5 belong to class 1. Okay. So you also see that if you look at class 1, see the related values 75977, and if you look at class 0, 33132. So direct separation is visible between these two classes, is it not? As far as if I compare this x1 value, uh, even in the graph also you can say direct separation is there between these two classes. Class 0, this blue labeled ones are class 0 and this red labeled ones are called as class 1. Direct separation is there. Now, this is my data set which has two variables x1, x2. There is a class variable y. 10 records are there. 5 records belong to class 0, 5 records belong to class 1. This is our example. Here, how learning happens in the LVQ model? First is initial codebook vectors. Second is update the codebook vectors for one pattern. Third is update the codebook for one epoch. So now we have these 10 records. From these 10 records, you can see here we had randomly taken the initial codebook vectors. We had randomly taken the initial codebook vectors. How many are there? 4. So 2 from class 0, 2 from class 1. See here, class 1 and class 0, 2 records, and class 1, 2 records we have taken. So we have randomly taken this x1 and x2. So 3, 7, 7, 3. You can see here we have taken this value, and then we have taken this value. Then we have taken I think this 7 wala 2 values. So this is my codebook vector now. What is my codebook vector? This is my codebook vector, and which has taken randomly from the training data set, which is taken randomly from the training. So the first step was initial codebook vectors. What is the next step? The next step is updating the codebook vectors. The next step is updating the codebook vectors. Let us look how updation happens. Okay. We have to specify the learning rate, is it not? We have to specify a learning rate, and the learning rate here in this example is chosen as 0.3, which is between 0.1 and 0.5. Okay. So what is the use of this learning rate? The use of the learning rate is to update the codebook vectors. Okay. Our first training pattern is x1 is equal to this, x2 is equal to this, y is equal to 0. Let us look at the codebook vector 3.39, 2.33. Okay, we are taking this one. Okay, the first record 3.39 and 2.33. Okay, now how do I update for this pattern? We have to calculate the distance of the training pattern to the codebook vector. Select the similar codebook vector. This similar codebook vector called as BMU. What is the long form for BMU? Best matching unit. Update the best matching unit to be closer to the training pattern if it has the same class, or take it away. Now I have what? See the flow. The flow is, this is my data set, 10 records. The next step is I have codebook vector. Codebook vector has randomly taken 4 records from the training data set. After that, the target is to update the codebook vectors for one pattern. How do I update it? Using Euclidean distance. So using Euclidean distance, we are finding out the distance here. Okay. So with what? So this is my x1. Okay. And this is my x2. Okay. And this x1 and x2, I am taking Euclidean distance for this content of the codebook vector. So x1 minus this x1, x2 minus this x2 whole square, square and whole square, and then square root. See here, hopefully you understood this. X1 minus x2 whole square, x1 minus x1 whole square, x2 minus x2 whole square. Then we have taken their sum, then we have found out the distance. Hope this is easy for you, right? What you are doing, you have x1 value, you have x2 value, okay, and you have these 4 randomly generated codebook vectors. Just use Euclidean distance formula to find the distance. This is the distance. Now among the distances, which is having the lowest distance? This first one is having the lowest distance, 1.55 11. It means what? We are speaking about this one. We are speaking about this one. Or speaking about this one. So it is the how do I put it? Best matching unit because it is having the smallest distance. Others are having higher distance. So codebook vector 1 has the smallest distance. So codebook vector 1 is the best matching unit. So what we concluded now from this codebook vectors, the first codebook vector, that is this 3.58 and 0.7 are the best matching vectors, Okay. Now best matching unit. After that we have to update this best matching unit. Okay. So for updating the best matching unit, you are either going away or coming nearer. Okay. So if you look at the first vector here, the class of this vector, best matching unit vector is 0. The class of this vector is 0. Okay. So the training instance class also is 0. Even the training instance class also is 0. Is it not? So they are matching. The classes are same. The classes are same. Now I have to update the attributes which should be closer to the training instance. If the classes mismatch has happened, they should go away. Okay. Now what the learning rate does? The learning rate actually controls how much change can be made to the codebook vectors for a single update. Okay. So here we are using a learning rate of 0.7. Actually this is high, but for this example to understand and for simplicity this high value is taken. Okay. Now how I am going to update the best matching unit value using this formula? Best matching unit for j is equal to best matching unit for j plus alpha multiplied by training j minus BMJ. Okay. Okay. So what is j? J is the attribute on the codebook vector being updated, which is x1. Alpha is the learning rate. Okay. And training j is the same attribute on the training instance, which is x1. Okay. So we are going to apply this learning rule and update the attributes of BMU, wherein we get this x1 value and this x2 value. Okay. So what we achieved was, with this we have completed an update for one training instant. Now after that what we have to do? Update for one epoch. We have to update. What is an epoch? Epoch is an iteration. Epoch is one pass, okay, through the entire training data set. How many records are there in the entire training data set? 10. Okay. So it means what? I am applying the above procedure for every training instance, okay, and updating the BM. We also need to pre-specify the number of epochs. Okay. That number can be anything. Okay. But we should know that after every epoch, the learning rate will be decreasing. What it indicates? Learning is happening. That's what it is indicating. And what is the formula for learning rate for every epoch? This is the formula for learning rate. Alpha multiplied by 1 minus epoch divided by max epoch. Okay. Now this learning rate applies to the current epoch. What is the size of the epoch? Because I will be pre-specifying the size of the epoch by max epoch. So the current epoch can be anything between 0 to max epoch minus 1. Alpha we already know. What is alpha? Alpha is the learning rate. Okay. And max epoch we know. What is it? Total number of epochs. Okay. So this way we'll be coming out with the updated codebook vector. These are the updated codebook vectors values. Okay. This process will be repeated maybe for another 10 to 20 epochs by reducing the learning rate, so that the codebook vector stabilizes. Now after that I need to make predictions with LVQ. Okay. So same thing, we'll be using the distance measure. Okay. Now we'll be returning the class value that becomes the prediction for our model. our model. So for every instance, we are making the prediction. Now to calculate the accuracy of this prediction, we'll be using this formula. Count multiplied by correct divided by count into instances into 100. Very easy. You can see here, these are the predictions, these are the actual classes, and you have 9 instances which are correct, and so the accuracy is 90%. Okay. So